Hello everyone, welcome to the sixth session of the QFT. I just need to do a correction from the last week, the video that we have about SU2 matrix. I just want to do a little correction. So what I mean by SU2, I meant a special unitary group. So a special unitary group have this feature that the determinant is equal to 1, not the trace of it. So I made a mistake. I said that's the trace, which is equal to 0, but that's the determinant, who is equal to 1. And that's a correction from last week, not the trace. Okay, let's start with the concept of solving the Dirac equation. So we have the Dirac equation, and we want to see how to solve this equation because we want to find the answers, plane wave answers, or free solutions. So these plane waves, they represent different modes of energy momentum. And the momentum is directly connected to energy in the free mode because there is no interaction. So we can separate the momentum and the space in that way. So imagine that I write psi of x as the multiplication of two terms, u of p and exponential. And the whole idea is that that particle is unshelled. So p0 squared is equal to p squared plus m squared. So that's a property of unshelled particle. So now we have this psi of x, and we want to see, so what is the psi of x in terms of the momentum answer. So that's basically the total answer is a linear composition or the linear summation of individual answers. And we are going to find those individual answers, psi of p, which consists of u of p times the exponential evolution factor. So, and p dot x is p0 x0 minus the vector p of vector inner product of p dot x. So the question is how to find u of p. What is the answer? If we find u of p, we can find the answer. That's a kind of a factorization method to find the answer. So u of p is two rows, one column, spinor. So we just write it down as right-handed and left-handed components, as we explained last week. So these right-handed and left-handed are terms that can be coupled through mass. And if there is no mass, there is no coupling at that time. So the advantage of writing down the equation like exponential term is that the derivative term, I d mu, can turn into the momentum operator, because the reason is that when we are taking the derivative from the exponential, that p can, when you're taking the derivative to x, that ip is going to come out. So there is this I term here for convenient, can come out, and basically turning the Dirac equation I gamma mu p mu actually. So the I is going to go away, and we are just going to have something without any complex terms. And then this is a matrix, right? The matrix that we have this p operator. This p operator is acting on that spinor, and this is equal to 0. Okay, how to solve this equation in general? So there is one particular way to solve this equation is to use the boost frame and take everything to the center of mass system. So everything taking to center of mass frame, CMF, and in the center of mass frame, we don't have any external momentum. So our momentum component is 0. So P is only have P0 term. So in any frame of reference, we have P0 and P, and then we boost it to the proper frame of reference. And that frame of reference is basically only have the energy component, not the momentum component. And that makes it super easy to solve the equation because we only have one variable here. But I mean, P0 and P are kind of dependent through mass. So P0 squared is equal to M squared plus P squared. But so for some convenient reason, it's easier to find it in the frame of reference, that center of mass frame of reference, and then boost it back to any particular frame of reference we want. So we have this Dirac equation. So now we take it to any frame, the frame of reference of center of mass, and we want to solve it. So the Dirac equation is invariant under any kind of boost. So when we are taking it into the frame of reference, the equation is so simple. We only have this gamma zero matrix. So now to solve this equation, we need to just write down the form of gamma zero. So the representation that we need, what representation we need for the gamma zero to be used here. So when we are using that representation, that is giving us the answer. So here we are just talking about the representation, and we have two representation in general that have this particular algebra that we discussed. We have the Dirac representation, and we have the Weyl or chiral representation of the Dirac matrices. So let's start from the Dirac representation. So in Dirac representation, the gamma zero matrix is on the diagonal terms, and then the gamma I is just basically the Pauli matrices on the other diagonal terms. And there is a minus sign also to the other component. In the Weyl representation, the gamma zero is different. So the gamma zero is off diagonal to the other diagonal term. So we have two unitary matrix, and then the gamma I is the same as the Dirac representation. So in the Dirac representation, we're only going to have the gamma zero term different. So gamma 0 m minus m acting on u of p0 is equal to 0. So it would translate it into this matrix that you have 2 minus m term on the diagonal term, because we are choosing the Weyl representation, and then 2 mass term here acting on u of p0 equal to 0. So now if we are thinking there is a right hand and left-handed, so you see left-handed p0 and then right-handed p0 is equal to 0, we're basically having two equations that are the same, because the coefficient of that matrix, if you look at it, doesn't make any two different equations. That's basically giving us one answer that is basically free to choose the basis of it. So we can write down as psi of left bar is equal to psi of the left-handed is equal to psi of the right-handed. So these are the kind of answers that are accepted. And P0 is obviously M, and we can just write down the psi of x for convenient reason as the square root of m. So the square root of m is representing how it's a function of P0, or how it's a function of mass. I mean, this functionality is just square root of m. And this is square root of m again for conventional reason, but you have two terms. We show them with psi, and these two psi's are equal to each other because that's the general answers. So the right-handed and left-handed components are acting in a similar way, and psi is any combination of C1 and C2 in the way that C1 star plus C2 star is normalized to having a proper normalization. So psi can be any arbitrary orientation of a spin. Any arbitrary orientation of a spin, but the left-handed and right-handed having the same behavior here. So the main point here is that there is one answer to Dirac equation, is the answer with the positive energy terms, and the right-handed and the uh, left-handed fermions are behaving in the same manner in time. Now we found the in answers in the rest frame. We want to find the answers in any frame of reference, any arbitrary frame of reference. How to find the general form of answer in any frame of reference. So now we need to boost it. So the answer to this question is that we need to boost it. So the rest frame answer need to be boosted to particular momentum frame of reference. Any frame of reference, it can be labeled with multiple things, with a certain momentum, a certain relative speed, and something that we call it here rapidity. So I'm going to talk about rapidity in a little bit, but you're going to see how rapidity is the parameter to label a frame of reference. So imagine that for simplicity right now, we want to um, only boost it along one frame of reference. So we just want to choose one particular axis here to boost the frame of reference, and that axis is going to be a z-axis. There is a certain reason to choose z-axis because the Pauli matrices on z-axis is a little bit more straightforward here compared to the x-axis and y-axis. So as you know, all of these axes are the same. They're not different. I mean, the final physics is the same. So it doesn't matter it's z or x, y. So, but z for uh, particular reason, but there is also reasons in heavy ion collision physics. In heavy ion collision physics, what you basically have is that we have protons, and these protons are having speed in the z-axis. So if you think when you collide these protons, there is this z-axis perpendicular to this circular frame, but this frame is spanning by the x-axis and the y-axis here. So it is kind of convenient scientific way to address the coordinates in the heavy ion collisions. So z-axis is the axis that we boost, and we are going to see boost along z-axis is similar to rotating on the spin space, and that's probably the beauty of it. So x and y are a reaction plane, and z are the axis along the collision. The collision happens in the z-axis, so anytime we boost, we want to boost along z-axis. One particular goal in heavy ion physics is to see how the final output are functions of the boost factor, or something that the energy center of mass energy represents. Okay, so U is a spinor, as we said, so we need to have the spinor transformation under the matrix S of lambda. So that's a representation of Lorentz transformation. So we basically have this U of P is equal to S of lambda acting on UP0. And this S of lambda, at least lambda is the Lorentz transformation. It's something that represents that Lorentz transformation. So it takes us from P equal to 0 to the frame of reference which P is equal to P. Another question is what is the characteristic factor for the boost, or what's the speed, but a proper speed in the relativistic way? What I mean by characteristic means yes, we are taking from rest frame to some frame of reference which the system have the momentum p, but momentum p or speed is not that characteristic. So in general, any boost have a characteristic speed, and we're going to show that that characteristic speed is called rapidity, because rapidity is a relativistically invariant speed, which you can add rapidity. We can add to rapidity, and rapidity is the additive variable when you're having two boosts along the same axis. Okay, so p rapidity or any speed. So I'm gonna write down this lambda of z as a function of gamma. So this gamma is not the Dirac matrices. This gamma is the relativistic boost factor. So it's a factor in relativity. Gamma is defined as 1 over the square root of 1 minus v squared over c squared. So this gamma is equal to the cosine hyperbolic of some variable eta that we call it rapidity. So this rapidity is also shown by y, and eta in heavy ion collision it's mostly y, and eta is used for showing pseudo rapidity. But anyway, here our purpose is to just show the rapidity. So we are going to use eta. It's a little bit more convenient. So this rapidity parameter is interesting. So this rapidity is an additive variable under the Lorentz transformation. So this is something that if we have two boosts, so if, for example, if we have two boosts, then we can add the rapidity for each boost. So imagine the parameter speed is not something additive under the Lorentz transformation, but imagine I have two boosts. So I have V1 and V2, and in non-relativistic limit, V1 plus V2 is going to be the total V, but this is not the case in relativity. So in relativity, V1 and V2 are not additive, but Y1 plus Y2 is equal to Y total. And you can prove why this pseudo rapidity is something additive. It's because of the exponential definition of it with respect to the gamma factor. So in gamma factor, we have this v squared in a special position under the square root of inverse. And then, so that's how rapidity is somehow bringing up those factors and trying to make them in a way that you can add them directly and use it. So this gamma is equal to cosine hyperbolic of rapidity. Let's say I'm using it with eta here. So gamma v is equal to sine hyperbolic of rapidity. So lambda z as a function of gamma has components here. So the 0, 0 component is gamma, and 3, 3 components for two axes that we have 0 time and 3 for the z-axis, and then you have this gamma v here. And we have 1 for the other axis, so it's identity. And again, it is for 3, 3, that one is for 0, 0, and these two are for 0, 3, and 3, 0. So these are the components and these identities here. That means that we don't have any boost along the other axes like x and y. Okay, that is equal to cosine hyperbolic of eta on the two diagonal term, and then sine hyperbolic of eta on the other diagonal term, and then the rest of it is the same. So that's basically a way that we can write down this lambda matrix, that it is additive under something, additive under eta. So if you multiply these two matrices, you're going to get some additive parameter with respect to the rapidity. Okay, now let's go to find out the form of a spinor representation of the Lorentz group. So when the way that we are rotating or boosting the spin. So we talked about this S matrix, and this S matrix have this form of it, omega mu nu, S mu nu. So there are some properties of omega mu nu and S mu nu is that they're both antisymmetric. So omega mu nu is equal to minus omega mu nu, and S mu nu is also antisymmetric. And you can prove that S mu nu is equal to minus S mu nu when we are exchanging the index, and it's going to be very helpful. So when we are boosting along z-axis here, we're trying to write down those terms down here. So we only have the components that mu is equal to 0 or nu is equal to 3. Again, mu for time and nu 3 equal to space, and vice so, and the inverse of them. So we basically are just dealing with time axis and the z-axis because we want to do a boost. I mean, no, the Lorentz group have also rotation inside of that. But here we're just talking about boost because we want to show that how boost is similar to rotation but in a spinor space. So this S of lambda z, I'm showing it with red here, is equal to the exponential of I omega mu nu. So this omega here, so instead of omega mu nu, I'm just writing down omega 03 and S03 plus I omega 30 S30. So we have this two term here inside of the exponential. So I have this I factor here. And I'm using this antisymmetric property. So each of those terms are the minus of the other term. So we have 2 minus, we have plus. So we basically have 2 times of the first variable here. So 2i omega 03 s 03. So now we only have like 2 term here. And that 2 here, inside of that, we can get rid of it by properly define S parameter out of the gamma matrices. So that's why you sometimes see 1/2 factor here to cancel out that 2 inside of that. So S03 is equal to I over 2. I don't remember actually, these 2 should be 4 right now or 2, but I think in some of the notations is 4 here, but we're going to go back to it. See, we have another canceling out. So we have, but the main core part of it is that this gamma 0 and gamma 3 are commuting with each other, should commute with each other. And it's the same for gamma 1, gamma 2. I mean, no difference in the physics of that because it's just the labeling of the coordinates. Now, let me write it down as So now what is this S0, 3 is equal to I over 2, gamma 0, uh, gamma 1, and it's gamma 1, gamma 0. Sorry, it's actually 3. Anti-commutation of these gamma matrices were 2 times of matrix, so 0 with any other components is the anti-commutation relationship is 0. So sorry, it was not 1, it's 3, so it's 0, 3. But again, 0, 3 or 0, 1 doesn't really have a difference, but the whole point is that there is this antisymmetric relationship between the order of these gamma. So gamma 0, gamma 3 is equal to minus gamma 3, gamma 0. So now we are just writing down as S 0, 3 is equal to I over 2. Now just let me write down this gamma 0 minus minus gamma 0, 3. So it's basically 2 again comes out. So again, this anti-commutation is simplified into one term using the anti-commutation formula. So these 2 again should cancel out. So the proper factor here is 4. So this 4 is going to cancel out 2 different 2's. And there's this first 2 on the omega and then the other one on the S. So S of 0, 3 is equal to I gamma 0, gamma 3. So gamma 0 was 0, 0, and then I2, I2, and the gamma I was sigma. Sorry, gamma 0 times gamma 3 is equal to 0, 0. Just want to make sure. Yes. To sigma. So sigma 3 minus sigma 3, 0. And then the final matrix multiplication is having minus sigma 3 and then 0 and then another 0 down here and then sigma 3. Okay, so this is the final matrix form of it. So now we have the exponential of minus omega 0, 3, this matrix here. Now I'm just gonna take that minus on back of it and turn it into a matrix. So we have the exponential of omega 3, sigma 3. So there is this minus sign. It's dissolved, and then we have minus omega 0, 3, sigma 3. So yeah, that's the exponential of a matrix. And now we're gonna see what's the benefit of having a diagonal matrix here, because if you have a diagonal matrix and then you have a function of that diagonal matrix, for example, the exponential of diagonal matrix. So what you basically do is to just get the exponential of that variable inside of that diagonal term, and then have the, so sigma 3 is a diagonal matrix 2, is 1, minus 1. So I basically need to calculate the exponential of omega 0, 3. So omega 0, 3 was also an additive parameter. So if we are basically having 2 boosts, omega 0, 3 is getting added. And omega 0, 3 is basically rapidity. So it's rapidity. It's additive under 2 Lorentz transformation along the same axis. So omega 0, 3 is equal to eta or y or rapidity. So I mean, y is something that we prefer to use in experimental physics, but never mind. We're going to show it here by eta. So this is y is more used, has more use. This eta here is just a notation. We can also use theta, but theta is not really good because we might make a mistake between theta and the angle, the physical angle for rotation. So anyway, S of lambda is equal to exponential of eta times those sigma 3. And then again, because those sigma 3 are diagonal matrices, so we can only take out the exponential term for the rapidity. So we are just... So by the way, the definition of rapidity is E plus PZ, E minus PZ. This is something that you can really prove easily. So S of lambda Z, or boost along Z-axis, is equal to the exponential of I omega 3 plus I omega 0 3, as we discussed before. So sorry to repeat that, but let me again write down this term as minus some variable rapidity times sigma 3. So now we have this S of lambda Z equal to this exponential matrix that we wrote down, rapidity minus rapidity sigma 3. And then now we can go into the diagonal term and just simply write it down as the exponential of rapidity times sigma 3, and exponential of rapidity minus rapidity, this time minus rapidity times sigma 3. And this sigma 3 is, that's why we are using sigma 3, because sigma 3 is diagonal here. That allows us in this particular case to do that operation here. And the rapidity definition is 1 over 2, the logarithm of energy plus pz, energy minus pz. So if pz is that axis, if we want to generalize it, E plus the magnitude of p and E minus magnitude of p, that particular frame of reference. And you're going to see why this logarithm definition is here, basically, because there is an exponential here. So we can just basically define minus omega, and this logarithm is helping us to take that minus sign inside with the power law. So we just basically can write down the exponential. So the exponential of those term here, so this factor 1 over 2 should go inside, because we want to get exponential of some logarithm. So 1 over 2 scale should go inside. So omega is equal to the ln or the logarithm, but this time the inside of that is a square root to take that, to absorb that 1 over 2. So the first term here is the square root of that fraction. And then for the other one, there is a minus sign. So we're going to flip the order of that. So E minus PZ, E plus PZ of sigma 3. And this is now the final version of S as a function of that particular energy momentum factor. So we know here E is equal to E squared is equal to PZ squared plus M squared, because we only have, so we have this unshelled particle, and then now we're just multiplying this matrix here. I'm just gonna copy this matrix. Should copy inside of it here. Just paste it. It's a big factor, and then in front of it I'm gonna write down the Spinor in the frame of reference. So there was this factor of psi, and then the final output is something like this. So this energy factor beside those right-handed and left-handed component. So we have this sigma 3 acting on the spin. So I'm just gonna take it out. Okay, put it right here. So it's a generalized form of the spinor that we have in any frame of reference boosted in certain direction. So sometimes it's good to just have one dimensional form of it because we are not making a mistake between the magnitude and each component. But now we also have to consider the negative answer frequency. So we assume at the beginning that we have this positive energy time. So it was a similar argument in the Klein Gordon. So we have this negative energy was corresponding to a positive energy that goes backward in time. So that represents an antiparticle, an antiparticle. So we consider the positive frequency answer, and then we have negative frequency answer in partial differential equation and differential equation. Usually when you have this certain first order or second order wave equation, you have two sets of answer. There are two sets of orthogonal series of answers, one with positive frequency and then negative frequency. So we basically try to look at minus IPX, and now we are just looking at the plus IPT, or psi of x is equal to V of P times plus IP dot x. So there's just like another sign for frequency, which in particular in physics means antiparticles, or instead of negative energy we say negative energy is equal to positive energy that goes backward in time, but there is no preferred direction for time. So again, similar operation to solve this differential equation. Instead of u, we are going to use v here, and these terms are just going to have a minor sign change. So we have minus m in all of them. The last time we have plus m minus m, and now we have minus m. And then the answer is v1 is equal to minus v2. So in these types of answers, the right-handed and left-handed are not the same, but they are minus of each other. So the right-handed is minus of the left-handed and vice versa. And then again, we found it in the frame of reference of the rest frame. And then now we're going to boost it into that particular frame of reference that we want, and we derive these factors here. So there is a sigma 3 also behind those Kisai terms. So I'm gonna put this sigma 3 behind the Kisai term. So that means that there is this matrix acting on Kisai. Okay. Now let's talk about the generalized boost direction. So we just look at the direction along z-axis. However, it doesn't really matter. But in general, if we have any arbitrary coordinate, any arbitrary direction for p, and then the sigma, then we are going to have this entity p dot sigma. So this sigma is representing the internal spin direction. So the way that we represent sigma 3, sigma 1, sigma 2, and this p is the geometrical vector for the momentum, direction of the momentum. So when you have the exponential of I omega mu nu s mu nu, which was the generalized form, you can always deduce it to some form of a spin rotation on some preferred direction. So I'm going to show it with like the inner product of the spin operator to the direction or the unit vector of the momentum. And this is something that we can simplify the whole expression, and that means the boost in momentum is equivalent to the rotation in the spin direction along p dot sigma. So for example, when we only had the z direction, we had sigma 3 but in any direction we just have to calculate p dot sigma. So this is somehow the momentum and spin are interconnected. So when we are boosting the particle along some axis, at the same time it looks like that we are rotating it on the internal spin structure, and that's how the momentum or space-time is interconnected with the spin configuration. And this S of lambda in general is going to be P dot sigma and then P dot sigma bar. And the difference between the sigma and the sigma bar is on the minus sign. So P dot sigma is P0 sigma 0 minus P dot sigma. So Pi dot Pi. And P dot sigma bar is P0 sigma 0 plus Pi sigma bar. Actually, I think that's the opposite. Sorry. That's the opposite. So the upper one is plus and the lower one is the minus. So sigma bar, something that has a minus sign inside of that. So at the end, the psi of x can be written as P dot sigma acting on psi, P dot sigma bar acting on psi, exponential of the minus energy or minus ip dot x plus, now we have the other answers. So the transformation is again the same, P dot sigma psi minus P dot sigma psi, and we have the time evolution term here, exponential of ipx bar. So we have this also factor of square root of m beside all of them. So we have, in general, that's the answer. The linear combination of these two terms are the answer for psi of x. Let me just cut it out and bring it right here. And for convenient reason, so we know psi is a 2 by 2. It's a 2 by 1, let's say, vector. So in the next session, we're going to see how to quantize the Dirac field. Now, since we got the answers, the plane wave answers, we can use them in order to quantize the Dirac field, and that's an important notation. Something that we're going to talk about is the how to do inner products of the psi field. So we need to introduce this new index of S. So psi is basically C1, C2, but for any convenient, any C1 plus C2 can be written as a linear combination of the bases that we have. We have 1, 0, and 0, 1. So this psi can be labeled with an index S, and this index S is just basically telling us which component of it to look. So we're using sigma S, an extra index, to see the component of psi S, and then we are going to pass this index S to psi. So we have psi of x of S. So you have this index S on top of that. And when we are writing down the whole term here, I'm going to write it down again. I'm going to use this index S. So now psi is not 2 by 1, it's just a number. So when we are looking at psi of particular S, we are looking at 2 by 2 components of it. One of them is coming from the right-handed and the other one is coming from the left-handed component of the field. And we're going to discuss more in probably in the next session what's the exact meaning of those right-handed and left-handed terms. So we have this index S, and this index S is going to be important when we are defining spin sum. The concept is called a spin sum. And you're going to see in general, this is the answer for each particular momentum. So the final answer is basically the sum over all the momentum states. So we can call it a psi of S of P, and each of those terms are P. So at the end of this session, we leave it up to here. And in the next session, we are going to talk more about probably answers of the Dirac equation, the spin sum, and probably in the next session after that, we are going to talk about the quantization of the Dirac field. Thank you so much.